So what I wanted to show you here was revisiting that three surface problem where we have one surface as the surroundings, but I'm going to modify it so that the emissivity of 1 and 2 are not black, right? It's no longer 1. There's some emissivity that goes with this. So let me first draw the resistance network that we had. So this is a node here, and out in the surroundings we have a node. And we have some geometric resistance between all these surfaces like this. So we would call this one up here RG, I guess this is node 1. So RG, RG 1 to 2. This is RG 2 to 3. This is RG 1 to 3. And then we have like the heat transfers. But one other thing that I want to, the point of this is I want to add something to this that's related to the surface resistance. So we know now that like this heat transfer across the surface is going to be related to not only like the view factors that are involved in the problem, the resistance due to the geometric factors, but also this like additional surface resistance. So we can represent the surface resistance as another resistance that sort of occurs before radiation leaves into this resistance network. So what I mean is this. So let's take, out here we've got some heat transfer, we'll call that Q dot 1. That is the heat transfer across the surface, meaning like from outside the radiation problem into the radiation problem. Okay, so to get that heat transfer into the radiation problem, it has to cross the surface, the surface resistance. So now we have this extra resistance that lives in here, and we'll call this RS1. Okay, likewise on the surface 2, we have, say we have in this direction, Q dot 2. It doesn't really matter the direction we draw. We just have to be consistent in how we write the equations. So this here would be RS2. And then on RS3 down here, call that RS3. And then from this, we have to sort out which of these nodes are related to the blackbody emissive power, which are related to radiosity. Okay, so we have our resistance network. The nodes on the surfaces I've already drawn. These nodes are radiosity nodes. So this over here is J2. This over here is J1. This down here is J3. Okay, so radiosity is the thing that's like exposed, right? If the node is a radiosity node, it is the node that's interacting with the surroundings. Okay, the thing that's now isolated from the surroundings would be the black body emissive node. So up here on the right, we'd have EB2. Up on the left, we have EB1. And down here, we have EB3. So because the surfaces are not black, there's additional resistance that removes the ideal black surface from the thing that's actually interacting. Okay? And so radiosity on the inside, emissivity on the outside. Some fine points now to deal with here. We have down here on the surroundings this fact, this emissivity of surface 3 or surroundings is equal to 1. What does that say about the resistance here? Right, this here is 0. So what is that, going back to what we talked about in the last slide, that's just saying actually this emissivity, or sorry, this radiosity here is actually EB3, right? So if it's not clear what I'm doing, but basically I'm saying, if you know that the resistance is 0, the radiosity is the same thing as the emissive blackbody power, so therefore we can just put the EB3 at the node where the radiosity was. And then we don't need to deal with J3 at all, right? It just sort of replaces it, okay? But in the other two cases, the two radiosity and the emissive power are different things, okay? All right, so let me just summarize the resistances here. So we remember our RG definition would be RG from 1 to 2. That is 1 over the area of 1. Let's just do it 1. Area of 1 times F12. Or if it was in terms of I and j, right, it'd be RGIJ is 1 over AI Fij. For the surface resistance, that would be like Rs of surface 1 would be 1 minus emissivity 1 over area 1 emissivity 1. So these both have units of 1 over meter squared. The resistance network can therefore be like consistent, like you can put all the resistances together in a single resistance network, unlike the resistances to like conduction and convection and stuff, which have to be connected in through boundary conditions. Yeah, question. Right, so the question is sort of how do you deal with conduction resistance or convection resistance for that matter. This is something that you have to fight with on the homework. So what you would do in that case is you would say, I'm going to establish, let's take, for example, this, let me just sketch it down here. So let's say we have this node is EB2. I know then that this node corresponds to some temperature T2, right? If I know EB2, I know temperature T2. In this direction, we have our RS2 and so on, right? In that direction. But let's say that out here you have some plate, and that plate has conductivity. So we call this like R conduction. And then out here might be some like T, I don't know, some other temperature you make up, right? Temperature of some surroundings or something like that. So the way that you would couple these two things together is you'd say, well, I know that the heat transfer across this surface here, this Q dot 1, that is the same heat transfer across the by conduction across the plate as will go through the surface and be included in the radiation problem. So you're coupling these things together by using the same Q dot. The Q dot is consistent. And you're also coupling it by saying this temperature here at T2 corresponding to EB2 is the driving potential for my conduction problem. So you have this extra equation and it sort of deals with that.